When we rotate a region around an axis to create a solid, we often default to disks or washers. However, when a region is bounded by functions of y but rotated around a horizontal line, or when solving for x is algebraically difficult, the method of cylindrical shells becomes our most powerful tool. Today, we will master how to visualize and calculate these volumes. Think of an onion or a roll of paper towels. Each layer is a thin cylinder. By summing the volumes of these infinitely thin layers, we can find the total volume of complex shapes. This technique is essential in engineering and physics for determining the mass and capacity of manufactured parts that have rotational symmetry. Before we dive into calculus, let's recall the geometry of a cylinder. If we unroll a thin cylindrical shell, it becomes a rectangular prism. Its length is the circumference, 2 pi r, its height is h, and its thickness is the differential change in our variable. Understanding this flattened shape is the key to building our integral. Choosing between methods depends on your slice. For a horizontal axis of revolution, the disk method uses slices perpendicular to the axis, requiring functions of x. The shell method uses slices parallel to the axis, which allows us to work with functions of y. This distinction is crucial for setting up the correct integral. Let's define our components for a rotation around the x-axis. The radius of our shell is simply the vertical distance from the axis, which is y. The height of our shell is the horizontal length of the function at that specific y value. The thickness of the shell wall is our differential, dy. These three pieces form our volume element. The volume of a single thin shell is its surface area multiplied by its thickness. This gives us the formula, volume equals the integral from c to d of 2 pi times the radius times the height, with respect to y. Because we are rotating around a horizontal axis, our integration must always be performed along the y-axis. Visualize the radius as a tether. As we move from the bottom of our region at y equals c to the top at y equals d, the radius of our shells increases. At any given point, that radius is just the y-coordinate. If the axis of rotation shifts away from the x-axis, this radius term will be adjusted accordingly. As we sum these shells from the inner radius to the outer radius, the integral accumulates the volume. This is mathematically more efficient than the washer method when the inner and outer radii of a washer would be defined by the same function, which often happens with parabolas or sideways curves. Now we set up the integral. We have 2 pi times the integral from 0 to 2 of y times y squared dy. This simplifies to y cubed. Integrating y cubed gives us y to the fourth divided by 4. We are now ready to evaluate this expression at our boundaries to find the final cubic volume. Plugging in our upper limit of 2, we get 16 over 4, which is 4. Plugging in 0 gives us 0. Multiplying our result by the 2 pi from the start of the formula, we get a final volume of 8 pi cubic units. This represents the total space occupied by our rotated parabolic shape. What if the region is bounded by two curves? Consider x equals y and x equals the square root of y rotated around the x-axis. Here, the height of our shell is the difference between the right-hand function and the left-hand function. In this case, that is the square root of y minus y. The curves intersect at y equals 0 and y equals 1, which become our limits. Our integral is 2 pi times the integral from 0 to 1 of the radius y, multiplied by the height, which is the square root of y minus y. Distributing the y across the terms will make the integration straightforward. The general form for a shifted horizontal axis at y equals k is 2 pi times the integral of the absolute value of y minus k times the height function. If the axis is below the region, use y minus k. If the axis is above the region, use k minus y. This ensures your radius and resulting volume are always positive. Let's look at a rotation around y equals 3 for a region sitting below it. The radius is now the distance from 3 down to y, which is 3 minus y. This adjustment is the only change needed in our shell formula. The height and the limits of integration remain determined by the shape of the region itself. A common point of confusion is which variable to use. Remember the golden rule of shells: the differential is always opposite to the axis of rotation's orientation, but the slice is parallel. For a horizontal axis, we use dy. For a vertical axis, we use dx. If your setup feels impossible, check if you've swapped these. Shells are often better when the functions are naturally given in terms of y, or when using the disk method would require splitting the integral into multiple parts. If you find yourself struggling to solve an equation for a specific variable, try switching to the shell method to see if the integration becomes easier. The most frequent error is mixing variables. If you are integrating with respect to y, every part of your integrand, the radius and the height, must be expressed in terms of y. Mixing an x radius with a dy thickness will lead to an incorrect and mathematically inconsistent result. Don't forget the 2π. Unlike the disk method which uses pi r squared, the shell method is based on the circumference of the shell. That 2π is a constant multiplier that comes from the geometry of the unrolled cylinder. Always write it outside your integral first so you don't forget it at the end. Since we are integrating along the y-axis, dy, our limits of integration must be y values. It is easy to accidentally grab the x-intercepts from the graph, especially if the region is square or symmetrical. Always double-check that your boundaries correspond to the vertical span of the region. To summarize, start by sketching the region and the axis of rotation. Identify your radius as the distance from the axis to a typical slice, and your height as the length of that slice. Determine your y limits, set up your integral with the 2π constant, and solve. This systematic approach works for any shell problem. Let's test your understanding. If we rotate the region bounded by x equals 4 and x equals y squared around the x-axis, what is the height of our shell? Think about the horizontal distance between the right boundary and the left boundary. I'll give you a moment to visualize the slice. The correct answer is B, for minus y squared. The shell's height is the horizontal length, which is the rightmost x value minus the leftmost x value. Since the radius is y, the full integral would be 2π times the integral of y times the quantity 4 minus y squared dy generated by VisionSolve AI.